Welcome to the first video on mechanics for the Year 13 portion of the Edexcel A-Level Maths course. So this topic is going to be called moments, and all moments are essentially the effect of a force when a force isn't applied directly to a pivot. So it's the turning effect of a force. So before we crack on and have a look at what this means and how it works with some worked examples, it's important to have some warm-up questions to get our brains in the right frame of thinking. So here are 4 questions to have a go at. As normal, you should probably know the drill by now. Pause the video here, jot down the questions yourself if you don't have these in front of you, and attempt them the best you can. Press play to see the solutions to these questions, which I'll try to guide you through as clearly as I can. Okay, so without further ado, let's have a look at question 1. So question 1, we have a diagram, and all we need to do is to indicate the shortest distance between the line L and the point P. So it really is as simple as this. Probably so simple you might be asking, why have I asked a question? It's going to relate to later. So the shortest distance between any point and a straight line isn't here or there. It's going to be the perpendicular distance between them both. So we just need to draw a line which goes to this dotted line L from P, and this, importantly, is going to be a right angle, like so. And working out this distance here from P to the line L, the perpendicular distance is going to be crucial to this topic, which we'll see later. Question 2, we have a force F defined as follows, where I and J are unit vectors in the x and y directions, respectively. So F equals I plus root 3J newtons. First of all, we need to calculate the magnitude of F. So we need to recall from year 12 that the magnitude of any vector, in this case F, is going to be the square root of the sum of its individual components, all squared. So here we have I, which has magnitude of 1. It's just 1I. So that's 1 squared. The magnitude of the j component is root 3. So we're going to do root 3. We're going to square that as well. So if we just plug these numbers into the calculator and see what we get, 1 squared plus root 3 squared, that gives us precisely 2. So the magnitude of F is exactly 2 newtons. Part B, we have to draw a force triangle to show F, and that has to include the magnitude of F, which we just worked out, its I component and its j component. And so the magnitude of F we can just include as 2 newtons, and F is acting in this direction where it's 1 along and 3 up. 1 in the x direction and root 3 in the y direction. And so F is going to look something, in fact I'll do a different colour, F is going to look something like this. Okay, so it's going along and up. So that's going to be a magnitude of 2 newtons. And going along, I'm going to do in a dotted line, is the I component, which was precisely 1, and going up was the j component, which was root 3. So 1 along and root 3. So that's just a simple triangle diagram illustrating F. So F is magnitude 2 newtons, and its I and j components are as such. So 1I along and root 3j going up. Part C, we have to calculate the angle theta that F makes with the unit vector I, which is going along, and label this angle on your diagram. So the angle that F makes is going to be here. So I'm going to call this theta. So this is essentially just right angle trigonometry. That's a right angle. So to work out theta, we can use any number of sin, cos or tan actually here. What I'm going to do is use the tangent function. So we know the opposite side is root 3. We know the adjacent is 1. So we can say that theta equals tan minus 1. Now tan is opposite over adjacent, so it's going to be root 3 over 1 which is just of course going to be root 3. So if we calculate this, if you can't remember how to do it, it's shift tan minus 1, then root 3 over 1 if you wish. So we're going to press equals, see what we get. We get exactly 60 degrees. That's an exact trig angle. So this one is 60 degrees. Now, so we've done C, I'll just label that there. Now D, this is the crunch. So D, it says calculate the magnitude of f multiplied by sine theta, which we just worked out, and magnitude of f multiplied by cos theta, which we just worked out. Then it asks, what do we notice? So magnitude of f times sine theta. Magnitude of f is 2, and theta is 60. So 2 multiplied by sine 60, we can work out fairly easily. 2 times sine 60 is root 3. Whereas magnitude of f multiplied by cos theta is going to be 2 cos 60. And if you try this on your calculator, you should see it's exactly 1. So in terms of what do you notice, well, what we should notice here, if we look at our diagram, is root 3 is the j component, and 1 was the I component. And so these are the I and j components, or to put it in the order it's come, this is the j and I components. So these are the I and j components of a force F. So we can extend this thinking further. So in general, I'm going to mention this later in these sets of notes and later in this video, we can generalize. So if we have a force or any vector, in this case I'm going to call it F, then going along like so, if we know the angle between is theta, then the component parallel to the I direction will always be F cos theta, and the j component will always be F sine theta. And this is going to be useful and crucial when it comes to resolving forces, which we'll talk about a bit this chapter and in depth the next chapter in the mechanics we do. So this is just an introduction to how we can resolve forces into two different directions. Question 3. We have ABC, which is a right angled triangle, with angle ABC being 90 degrees as such, BAC being 30, and AC being 5 root 3, like it says in the diagram. Find the exact length of AB. So what side is AB? AB is this one. So I'm going to call this X because I don't know it. Now again, this just goes back to right angle trigonometry. So a big focus on trigonometry in this warm-up because this topic is going to be very heavy on knowing the trigonometry from the GCSE. So in terms of the angle we know, which is the 30-degree angle, opposite to the angle, which I'm going to call the O for opposite, we don't know the opposite side. We do know the hypotenuse, which is this side. The other side is A. So we want to find A, and we do know H. So in terms of SO, CA, TOA, we pick a triangle which includes the side we know, H, and the side we want to know, in this case A. So which of SO, CA, or TOA includes both H and A is going to be CA for cos. And so what we do here is we recall the CA triangle, Now we want to work out the adjacent side. We want to work out x, which is the adjacent. So essentially we cover up the adjacent, and what's left tells us what to do. So in other words, the adjacent, which is from A to B, is C times H. C stands for cos of the angle, so that's cos of 30, whereas H, for hypotenuse, is 5 root 3. So we can just calculate this now fairly straightforwardly. Cos 30 multiplied by 5 root 3 gives us 15 over 2, which we can say is 7.5. So we have here 7.5 centimetres. And last but not least, question 4 of a warm-up. Question 4, again, is quite simple. This is just seeing if you can remember the sizes of units, essentially. So we've got diagrams below showing two seesaws modelled as light rods AB, held at rest and pivoted at a point O, as seen here, which is the midpoint of AB. Masses rest horizontally on both sides of the seesaw. Both systems are released from rest. Indicate with an arrow the direction in which each seesaw will tilt. So let's put these into standard units, if not already. Kilograms is already the SI unit, so we can leave that as 0.4 kilograms. 4,000 grams, though, is not. So to convert from grams to kilograms, we divide by 1,000. So we see that's 4 kilograms. So if that's 0.4 kilograms, and this is 4, obviously 4 is greater than 0.4. So when these are released, the heavier side will tilt downwards, and so it's going to go in this direction. This next one, B, 0.015 kilograms, fair enough. To convert from grams to kilograms, again we divide by 1,000. So if we do 1.5 and divide it by 1,000, let's see what we get. We get 1.5 times 10 to the minus 3. Now, if your calculator's doing this and you don't like it, what we can do is press, I'll just show you here on my screen. We can press Shift, Setup, go to number format, number 3, press normal mode, and then press option 2. Now if we try it again, we'll get it as a decimal. So we get 0.0015. So 1.5 grams is 0.0015 kilograms. 0.015 is greater than 0.0015, and so in this case, the seesaw will tilt this way. So hopefully we are thoroughly warmed up now, or at least a bit warmed up. So let's have a look at the main body of this section. Before we get started proper, I just want to talk about how we can resolve forces into directions which are parallel and perpendicular to a point. So, we mentioned this in warm-up question 2. So with warm-up question 2 illustrated, a force can be broken down, which can be called resolved, into two other equivalent forces, usually these are called components, acting in perpendicular directions to each other. So in general, a force F can be resolved as follows. So warm-up question 2, if we have a force going at an angle, then the horizontal component is the magnitude of a force multiplied by the cosine of the angle made by the horizontal and the force, and the vertical component, the J component, is the magnitude of a force multiplied by the sine of the angle made by the force and the horizontal. Now of course, this force, or any force, will originate from a point. So in this case it originates from this point here. So what we need to do is to have this here mirroring the reality. So these components, F cos theta and F sin theta, need to be replaced to originate from this red point. So all we need to do here is to translate F sin theta, so rather than it being here, starts from this red dot. So the next step, place both components at the force's origin, and we get this here, which is far more useful. So by resolving forces, it sometimes makes moments questions easier, which I'll explain later. So moments. What is a moment apart from an expression for a period of time? Well, it's a physics term and also therefore a mechanics term as well. So in this chapter we'll begin to see the effects of forces on rigid bodies rather than just particles. This means that to consider moments we need to think about the following: the size, or in other words the mass of the body in question, the position where any given force is applied, and also the turning effect of a given force on the rigid body. And it's the turning effect of a given force which we call the moment of a force. So how can we define moments? Well, the moment of a force measures the turning effect of the force F on a rigid body. It is worked out by taking the product of the magnitude of the force and the perpendicular distance d from the line of action of the force to the axis of a point of rotation, often called P. It's often called P because P stands for pivot. So a pivot is like a hinge where things move around or rotate about. So here's a diagram to illustrate it, and so we can work out here the moment of this force F. So the moment of F will be the magnitude of F multiplied by the perpendicular distance from the line of action of a force to this P. So this here is a right angle, so it's just magnitude of F multiplied by D, because D is already given as the perpendicular distance. It's almost as simple as that. I say almost because there's a little thing to bear in mind, and it's the following. The moment of a force can be either a clockwise or an anti-clockwise direction. So here, relative to P, because F is pushing this way around, if it were a circular motion, it'd be going around here like so. So that's going to be going anti-clockwise. So we also need to include whether it be a clockwise moment or an anti-clockwise moment. And that's an important point to bear in mind and to remember. So let's be thinking of this intuitively. So I mentioned now that moments can be going either clockwise or anti-clockwise. So let's imagine pushing open a door. So this is going to be a bird's eye view of a door. So two diagrams, the same door in each. So I'm going to label here the pivot of the door, P. So in plain English, this will be where the door's hinged. So the door's attached here to the wall or whatever. So let's imagine this door can move either this way or that way. So if a person comes along and tries to open the door by pushing it from this side with a force I'm going to label unimaginatively as F, then obviously this force F will have a clockwise moment because the door will swing this way. On the other hand, if someone's coming the opposite way, hopefully not at the same time, because that could be quite painful, and is trying to open the door from this direction, oops, that's slightly at an angle. Okay, so I'll call this one F as well. Then of course, in this case, the door would be moving in this direction, which would be anti-clockwise. What if a force is acting at an angle though, not perpendicular to the pivot? So just to mention this, in the previous definition, in the above notes, in the previous couple of minutes in the video, the given distance was perpendicular to the line of action of a force. But when this isn't the case, trigonometry needs to be used either to find the perpendicular distance or to resolve the force appropriately. So I'm going to show you two ways this can be done. So method A, just using the definition of moments. So again, the moment is the magnitude of a force so that's going to be obviously F multiplied by the perpendicular distance between the line of action of the force and P. So in these cases, we might not actually know the perpendicular distance that will need to be calculated. So what we need to do is to draw on a line, like so, which is perpendicular to F. So we need to find this distance here. So I'm going to call this distance, in fact, nothing. I'm just going to try and work out what this is. Okay, so relative to the angle we know, in this case theta, we need to work out the opposite side. So if we have a force triangle and we know the hypotenuse, in this case d, the opposite side will be d sine theta, and the adjacent side, this one here, would be d cos theta. And so this one here is just simply d sine theta. Now sometimes drawing in these perpendicular lines can be quite awkward, especially when it's not easy to draw on. Sometimes it means extending the line of action of a force. It can get quite ugly and hard to picture how to draw them. In those cases, sometimes it's best to resolve a force into two perpendicular directions. So, like I mentioned before, this force can be resolved into two directions, one which is parallel to the line of action of a force. So if I go for example, a line here, going along towards P, and also a line going up. So this force can be split into two, and it can be imagined as having a component going parallel to and through the pivot. The one which goes along will always be cosine of this angle. So this one here would be F cos theta, and this one going up will be F sine theta. And if ever you forget this, it's always worth just making a note of things you might well forget. If you have any force F, and you know the angle it makes, let's call the angle it makes theta, then we can always resolve into two forces, one which goes along, which we can call F cos theta, and one which goes up, which we can call F sine theta. So that's always worth referring to and remembering. Make a note of that if in doubt. So, returning to the diagram now. So here, thinking of F instead as vanishing and being these two individual forces, then what force, what moment would F cos theta have relative to P? Well, the moment is the magnitude of a force multiplied by the perpendicular distance between its line of action and the pivot. But if F cos theta goes through P, then its line of action has a distance of 0 away from P, because its line of action is going through P itself. And so this here will have 0 moment. And the only force which will have a moment will be this vertical component, F sine theta, which, because of the way we've resolved it, is already now perpendicular to this distance here, d. So, thinking of it this way, the overall moment we'll have will be F sine theta, this force, multiplied by the perpendicular distance of that force from P, which from here to P has already been given as d. So F sine theta times d, or d sine theta multiplied by F, is one and the same. I suppose for the sake of being consistent, I should do this, but I mean that anyway. Okay, so this and that are one and the same, just different ways of thinking of the same problem. Use whichever method you prefer. Some questions it's easier to do this, other questions it's easier to resolve the forces, For these examples, I will focus on using the actual dictionary definition of a moment, although for the last example, worked example 5, I'll mention how resolving forces could have been used as well. So let's have a look now at some worked examples together. So, worked example 1a, find the moment of each force about the point P. So for this one, the moment of that 6 Newton force is the magnitude of the force, it's a 6 Newton force, multiplied by the perpendicular distance between this force line and P. We already know the perpendicular distance, it's told us it's 3, so it's going to be 6 multiplied by 3, 6 times 3 is 18. Now the units are the units of force, newtons, multiplied by the units of distance, which here are meters. The Newton meter is the SI unit of a moment. And finally, of course, we need to give either a clockwise or anti-clockwise direction relative to P. This force here is going to spin round this way, and so it's anti-clockwise. And so that's all we need to do for that one. For 1b, we need to work out this distance here between P and the line of action of the force. And so this again is just right-angled trigonometry. We know the hypotenuse is 8. We want to work out the opposite side. Like I mentioned before, the opposite side is going to be the hypotenuse multiplied by sine of this angle. In case you're wondering, in case it was a different question or different context, if you wanted to work out this side here in blue, that would be 8 cos 35. But here we just need 8 sine 35. So for this case, the moment is the magnitude of the force, which is 12, multiplied by the perpendicular distance in between P and the line of action of the force, which is just 8 sine 35. So 12 multiplied by 8 sine 35. Get the calculator if in doubt. So 12 times 8 sine 35. What does that give us? Well, that gives us, to 3 significant figures, 55.1 Newton meters. Only this time, this force is spinning around that way, and so it's a clockwise moment. Let's check out another worked example. This time we've got 2 forces acting at the same point. So the diagram shows 2 forces acting on a lamina. So what is a lamina? I'm just going to mention this now. A lamina is a flat 2D surface of negligible width or thickness. So its thickness can be ignored. It's like an infinitesimally thin sheet of paper or something like this. So a lamina is like a sheet of paper a nanometer thick. That's what it means by lamina. Don't let the words throw you off. That's all it means. So basically, maybe this is like a constructions question for GCSE. So the compass is held at P. Some classmate is trying to turn the tracing paper around this way with a 5 Newton force. Someone else is arguing, no, it's an anti-clockwise rotation, you need to turn the tracing paper this way, and they're trying to push at 8 newtons. So the lamina could be like tracing paper. It doesn't really matter, that's all lamina means, it's a flat 2D surface. So in this question, what we need to do is to find the moment of each of the forces about point P. So essentially we've got 2 forces, we've got a 5 Newton force and a 8 Newton force. I'm going to take these forces separately and do them separately and on their own. So for the 5 Newton force, let's consider this one. So the moment of this one is very easy to work out because we're told this perpendicular distance from P to the line of action already. It's 2 meters. So that's just going to be 5, the magnitude of the force, multiplied by the perpendicular distance, which is 2. 5 times 2 is 10 Newton meters, which is going to be in a clockwise direction. Simple as. Whereas the 8 Newton force will be working in an opposite direction. This force is going to create a anti-clockwise moment because relative to P, it's going this way round instead. This one, though, hasn't been given as a perpendicular distance. So what we need to work out is the perpendicular distance from P to the line of action of this force, which is this line I've drawn in red. So again, relative to the angle we know, the 50-degree angle, because we know this angle here and the hypotenuse is 2, then again, the opposite side is the hypotenuse, 2, multiplied by sine of the known angle. So this distance from P to the line of action of the force, this perpendicular distance is 2 sine theta. So the moment of this 8 Newton force is the magnitude of it, which is obviously 8, multiplied by 2 sine theta. So 2 sine 50, I mean to say. So 8 multiplied by 2 sine 50. That gives us a turning force of, to 3 significant figures, 12.3 in a anti-clockwise direction. 12.3 Newton meters anti-clockwise. So this should now beg the question to you. If we have a point P and we have 2 or more forces offering a turning force or moment each, could these moments be combined into an overall resultant moment? For example, if you've got 10 Newton meters clockwise and about 12 anti-clockwise, isn't that going to be like about 2.3 newtons anti-clockwise overall? Well, yes it is, and that's what this next sub-chapter is going to look at, resultant moments. So this is a warm-up, essentially, to the next 3 worked examples about resultant moments. So, when there are several, 2 or more, coplanar forces, coplanar means acting in the same 2D plane, coplanar forces acting on a body, we can determine the overall turning effect around a given point by choosing a positive direction, which is either clockwise or anti-clockwise, and calculating the sum of the moments produced by each force individually. The sum of the moments acting on a body is called the resultant moment. In the same way, if you need to work out the overall effect of multiple forces, the overall effect of all forces is the resultant force. It's the same idea with moments. Let's have a look at the first worked example and how we might calculate a resultant moment. So question 3, keeping it simple, all these forces are perpendicular to P, the line of action. So we've got a diagram showing a set of forces acting on a light rod. Calculate the resultant moment about the point P. My suggestion here would be to work out the clockwise moments and also the anti-clockwise moments. So relative to P, which is here, the only one which is going clockwise relative to P is this 5 Newton force, because 5 newtons relative to P will be spinning around it like this. So, clockwise we have the 5 Newton force. The moment, because of its force, is the magnitude of it, 5, multiplied by the distance of this force from P. This perpendicular distance is 2 plus 1, which is 3. 5 times 3, that gives a 15 Newton meter moment. whereas going anti-clockwise, we've got two forces which would give an anti-clockwise moment. First of all, we've got this 4 Newton force here, which is 1 meter away perpendicularly. So this force here, the 4 Newton, would offer a moment which is 4 multiplied by 1, which is 4 Newton meters. And the 3 Newton force on the far right hand side would have a moment of 3 multiplied by the distance of this force from P, which again is 1. So 3 times 1 gives 3 Newton meters. So from these two, hopefully we can see that the total anti-clockwise moment is 4 plus 3, which is 7 Newton meters. In terms of determining the overall resultant moment, I would pick whichever has the largest moment as the positive one. So obviously the clockwise 15 is greater than 7, so pick the clockwise as positive. So therefore the resultant moment is going to be the clockwise moment, 15, minus the sum of all anti-clockwise moments, which is 7. So 15 minus 7 gives an overall net resultant moment of 8 Newton meters going clockwise. Let's check another example out. This time we've got forces acting at an angle. So this time we've got a diagram showing three forces acting on a light rod. Calculate the resultant moment about the point P. So same idea, different worked example. So we've got 3 forces. We've got a 5 Newton force, we've got this 6 Newton force, and we have a 4 Newton force. So we can see here that the 6 Newton force is already acting a perpendicular direction to P, because this line of action 6 and its point of origin here to P is a perpendicular distance, whereas these ones are acting at an angle. So what we need to work out for the 5 and 4 Newton force is the perpendicular distance to P. Whoops, I don't want a line like this, so what I'm going to do, right, so I need to work out that distance for the 5 Newton force and that distance for the 4 Newton force. So again, let's keep it simple. So work out the clockwise moments. The only one which is going to give a clockwise moment for P is this 5 Newton force. So the moment from the 5 Newton force is its magnitude multiplied by its perpendicular distance from its line of action to P. So we need to work out this distance here. So if this were a triangle from here to there to there, the hypotenuse opposite the right angle would be 4. That bit's 1, this bit's 3, so the total length of this bottom side is 4. Okay, so that's 4. In fact, I'll label that on just so it's not confusing or ambiguous. From here to here, that's a length of 4 meters. So I want to work out the length of the side opposite the 80-degree angle. If I'm working out the opposite side, it's going to be the hypotenuse, which is 4, multiplied by sine of the angle. So it's going to be 4 sine 80. So for this 5 Newton force, the moment is 5 multiplied by 4 sine 80, which is, let's see, 5 times 4 sine 80. We get 16.696. sorry, 19, I can't read, 19.696. I'm giving it to more decimal places because this isn't our final answer yet. We also now have two anti-clockwise moments to consider. So the first one is this 6 Newton force. This 6 Newton force is 3 meters away from P. So the magnitude of this moment will be 6 multiplied by 3, which is 18 Newton meters. And for the 4 Newton force, I need to work out the perpendicular distance from the line of action of the force to P, this dotted line here. Again, looking at this triangle here, I know that the hypotenuse is 3 meters. I'm wanting to work out the opposite side, because I want to work out the side opposite to the 40. Like I've said before a few times now, if I was working out the adjacent side, it would be the hypotenuse cos the angle, so the adjacent side would have been 3 cos 40, but again, because I want the opposite side, it'll be hypotenuse 3 multiplied by sine of the angle, so 3 sine 40. So the moment from the 4 Newton force is the magnitude of the force itself, 4 multiplied by 3 sine 40. Let's see what that gives us. 4 times 3 sine 40. That gives us 7.713 roughly. So I'm going to call it 7.713 Newton meters. So the overall total anti-clockwise moment, 18 plus 7.713, which is going to be 25.713 Newton meters. So obviously you can see that the anti-clockwise, 25.713, is larger than the clockwise, and so we can take the anti-clockwise as positive, because normally, by and large, it's best to end up with a positive moment and then just call it whichever direction it is, rather than saying it's a negative moment clockwise, which should mean it's a positive anti-clockwise moment. It's just more confusing. So the overall moment, the resultant moment, is going to be the 25.713 meters acting in the anti-clockwise direction, less the 19.696, which is opposing it. Let's just use the calculator to check that one out. So 25.713 minus 19.696. Now at this point we can round off, and that's okay. So it's about 6.02 Newton meters to 3 significant figures, and it's acting in an anti-clockwise direction. I'm now just going to show you a final worked example to illustrate the method of just resolving forces instead as well. So worked example 5, we've got this diagram here showing two forces again acting on a lamina. These forces are originating from the same point, which doesn't matter, that's still fine, that can happen. Calculate the resultant moment about the point P. So first of all, we're going to notice here that the 7 Newton force is going to have a clockwise effect, whereas 4 Newton force is going to be acting in an anti-clockwise direction. So clockwise, we're going to have the effect of this 7 Newton force. So what we need to do to work out the dictionary definition of a moment is to calculate the perpendicular distance of the 7 Newton force's line of action from P. So we need to calculate this distance here in red. In the same way, for the 4 Newton force, we'll need to calculate the perpendicular distance from that line of force's action to P, which we need to maybe extend slightly onwards. And so doing that, what we're going to do here, and this is why it can be a bit more complicated doing it this way. So if I extend that line of action a bit longer, and then do that like so, then we can see that that's approximately perpendicular. Okay, and both these hypotenuses are 8 meters. So again, I'll just add in 8 meters on a solid green line. So acting in the clockwise direction is going to be the 7 Newton force. So this distance here in red, I need to work out the opposite side to this 25-degree angle. The opposite side is going to be the hypotenuse, which is 8, multiplied by sine of the angle. So it's going to be 8 sine 25. So for the 7 Newton force, its moment is 7 multiplied by this red distance here, which is 8 sine 25, which is, let's see, 7 times 8 sine 25. That gives us 23.667-ish. And that's acting in a clockwise direction, like I've said. Whereas, of course, this 4 Newton force is acting in the anti-clockwise direction. So I need to work out the distance from the 4 Newton line of action to P. So I need to work out this blue distance here. Again, I'm working out the opposite side of this right-angled triangle. The opposite side is going to be the hypotenuse of this triangle, which again is 8. 8 is a shared side of both these triangles, this time multiplied by sine of 35. So for the 4 Newton force, this moment relative to P is going to be the magnitude of a 4 Newton force, which is just 4, multiplied by 8 sine 35. So 4 times 8 sine 35 gives us 18.354-ish. So it's 4 Newton force. It's got that moment. So hopefully it's easy to see that the clockwise moment will prevail because 23 is greater than 18. So therefore, the resultant moment will be clockwise. So start with the bigger one, start with the clockwise, then minus off the anti-clockwise, and the overall moment will be in the clockwise direction. So 23.667 minus 18.354. That gives us, to three significant figures, 5.31 Newton meters, and it's going to be in the clockwise direction. Let's now see another way that we could have tackled this question by resolving forces. So, what if we resolved instead of doing what we did here? So, instead of doing that, if we resolved, what we could have done is resolved the 7 and 4 Newton force in a direction which was parallel and going through P, and a direction as well which is perpendicular to P. So if I have a look at this 7 Newton force first of all, and colour code this one in red, And what I could have done is resolved this one in a direction which is parallel to P and going through P, like so. And also done it in a direction perpendicular to P, so going up like this. It's not quite perpendicular, that's better. So like I mentioned before, if we resolve in these directions, then the component which is going along the bottom of the angle will be the hypotenuse multiplied by cos of this angle. So in this case, 7's the hypotenuse, okay? This is the adjacent, that one's going to be the opposite. So this side here, in the dotted red, would be 7 cos 25. And this one going up here will be 7 sine 25. So for the 7 Newton force, which has now been resolved into 2, because it's been resolved into 2, we can essentially ignore the original force and think of it in its 2 components. So the 7 cos 25 force, because it's acting through P, the distance of the line of force from P is 0 because it's going through P itself. So this will have a 0 moment. The only moment will be this component here from the 7 sine 25. So this 7 sine 25 will give a moment. It'll have a moment effect, and the effect of this 7 sine 25 force will be its magnitude, this, multiplied by its distance from P, which we can see here is 8. So multiply that by 8, because 8 is the given perpendicular distance, like we can see. And we have here 7 times sine 25 by 8. We get 23.667, like we did before. Then if we consider the 4 Newton force in the same way, and resolve that one. So again, this time we can resolve it both parallel and perpendicular to this line of action going along P. So I can call it this here going along. It's quite hard to see the difference between the red and the blue because they're superimposed one top of the other. But this one here, because it's going along, and that would be for cos 35. That component's for cos 35. And the component going down like so will be for sine 35. So again, like the 7 Newton force, the original 4 Newton force can be forgotten, and we can consider it as the net sum of these 2 components instead. So the 4 cos 35 component will offer no moment relative to P, because 4 cos 35 is going through P, so it has no distance away from P. The only one which will offer a moment will be the 4 sine 35 component. So this moment relative and due to this force will be the magnitude of this component, 4 sine 35, multiplied by the distance of 4 sine 35's line of action from P. Because it's been resolved perpendicularly, we again can see that this distance from here to there is again 8. So this time we have 4 sine 35 again multiplied by 8, and that will give us, let's see, 18.354. That should be in a blue colour. There we go. So again, as before, the net component, the net moment, will still be the same. So it'll be 23.667 subtract 18.354, which again, if you calculate this, will still give us 5.31 Newton meters clockwise. Now, that method might confuse you, A, because it's not as common, and B, because I've only shown one worked example using this, rather than the whole 5, where I've been taking the perpendicular distance from the line of action of a force to the pivot. So this is useful, it just requires a bit more practice and exploration, so don't give up on this method. Have it in your arsenal, because the more approaches you have for any one given question, the more versatility you'll have going into your exam, which will maximise your chances of scoring maximum marks in any given situation. That's all the worked examples from me anyway, so here are my suggested exercises for you now. So in your Year 2 Stats and Mechanics books, if you can attempt these questions, exercise 4A, 1BD, 2AC, and question 5. You can do questions 3 and 4 as well for additional practice. And then move on to the resultant moments section, exercise 4B, question 1, ACE, 2BDF, and questions 4, 5, and 6. As ever, if you're stuck, please do ask me in class or leave some comments in the comments section. I'll endeavour to get back to you, or drop me an email, or failing that, please do try and find me outside of class and I'll try to help you out as best as I can. Thank you very much for listening. Do enjoy your maths and please do consider subscribing to the channel. It's very nice if you do so. Thanks again, and I'll hopefully see you all soon. So goodbye for now.